Basically, this challenges on channel estimation using machine learning or model-based approaches, more conventional signal processing techniques, because our goal is to compare both and to see what can we gain with the different approaches. The channel estimation challenge that we are gonna describe is site-specific. So either if you are using channel estimation based on signal processing techniques, conventional signal processing techniques, or machine learning approaches, you're gonna have some information about the specific propagation environment where you need to estimate the channel. And that information will be used for both types of techniques. Otherwise, the comparison wouldn't be fair. We are doing this because current machine learning techniques are not working very well yet. When you train in a different site, when you train in a site and then you test in a different site. So we wanted to give a chance to data-driven approaches to perform the best they can. And we know that more work is needed to transfer this knowledge about the site and to make a given architecture work in a different site. But to start, this is the first year we're having the challenge. I think this is a good choice, a good trade-off for comparing machine learning approaches and data model-based approaches. We are also going to consider a given type of architecture, and we are going to consider millimeter wave frequencies. So when we work at millimeter wave, we need a MIMO system. That's a must. We cannot have enough gain if we only have a single antenna. And we need beamforming gain at both sides, usually at millimeter wave, at the transmitter and at the receiver side, because the wavelength is very small. So if we just have one antenna, the antenna aperture is going to be extremely small. We cannot capture the energy, and that's why we need arrays. The arrays we need have to be large. We cannot use small arrays like in LTE, for example, where MIMO is a feature of the standard, but the maximum number of antennas is only 8. For operating on millimeter wave, we need to use much larger arrays. We are talking about 64, 128 antennas at the base station, maybe 16, 32 at the device. In different environments, not cellular, these numbers can vary a bit, but in general, we need large arrays. And when we use large arrays, we cannot use conventional MIMO or digital MIMO because the power consumption would be very, very high. We cannot afford that power consumption, especially at the device side. So to operate on millimeter wave, we can have an analog architecture or a hybrid architecture. We could also have an all digital architecture with very low resolution ADCs. That would be a possibility too, because the bottleneck in the power consumption is in the ADCs. But the usual approaches are the analog architecture and the hybrid one. There is more literature about them. And I think low resolution architectures for millimeter wave are a very promising alternative, but are still not mature enough to be used in a standard, for example. So we are going to focus in this challenge in the hybrid architecture. We think it's a very interesting trade-off. We can send several streams. With the analog one, we can just send one stream because we only have one RF change. So with the hybrid architecture, we can send several streams. We have 2 stages for precoding and combining. So we have more flexibility to deal with multi-user interference, for example, to deal with multiple streams. And this is a choice that has been considered in current cellular standard for 5G. So it's not that we are doing or considering this architecture without thinking of the commercial applications. Hybrid millimeter wave is part of the features of 5G, but the main challenge is how to configure this architecture with low overhead, with very few training symbols. That's really an interesting problem and complicated, because first you have a very low SNR before acquiring the channel information. You cannot be informed the signal in the appropriate channel directions, in the strongest channel direction, so your SNR is low. Then you cannot access directly the output of the antennas, because you have the RF combining stage, which is acting as a compression stage and is mixing all the information coming from the different antennas. So you may have maybe 64, 32 antennas, but maybe you only have 4 RF chains. And that's the information that is at the output of the ADC and available for you to estimate the channel. So it's a much more complicated problem than the usual MIMO channel estimation at lower frequencies. 5G doesn't really estimate the high dimensional MIMO channel that I'm talking about. What 5G does is configures the analog and digital precoders and combiners using a beam training architecture, a beam training protocol. In this beam training protocol, what we do is we consider a given set of possible beam patterns at the base station, a given possible set of beam patterns at the user side, and there is a exchange of information between the base station and possible users around, and the users listen to the possible beam patterns that also send synchronization signals, and they try to find which is the best beam pattern. If they are able to receive information from more than one beam pattern from the base station, then they have to measure some metrics like well, related to the signal to interference noise ratio, basically. And they choose a beam, and then when they choose a beam from the base station, they reply to the base station and they say, well, I'm going to choose this beam, and they know which resources in time and frequency they have to use, because that information is also encoded in the beam that the base station is, and the synchronization signals that the base station is using. And then the user also can refine a bit the beam and use a narrower beam than the one it was using for listening. And basically it's trying different combination of transmit and receive beams, as you can see in the figure, and pick the best one, the best in terms of signal to noise ratio or signal to interference noise ratio. And the problem with this design is that it requires a lot of overhead. There are papers which have studied the number of training symbols or the training time, and it depends if you are using of a hybrid architecture or an analog one. Can be in the order of several seconds for an analog architecture, in the order of almost seconds to like many milliseconds for a hybrid architecture. So it's really not appropriate when we have mobility at the device, because when we are able to configure the link, the channel has already changed. So it's really a problem. To configure the precoders and combiners in a hybrid architecture, we could do the following. We could use a beam training protocol like the one I explained before, like the one in 5G, and configure with that the analog precoder and combiners. That means choosing a beam pattern at the transmitter from a given codebook, the best one, and choosing a beam pattern from a given codebook at the receiver for the combiner, and configure the analog part, the analog precoder and combiner. And then what we have is an equivalent channel, because we can define a channel which is the combination of the analog precoder, the physical channel, and the analog combiner, and all the filtering effects that can be in the middle too, and other hardware effects. So we can use, we have, let's say, configured that analog part of the link. And what we can do is to try to configure now, to try to estimate this low dimension channel, because as I said, we are going to have a small number of RF chains. Maybe the access point or the base station can have 8, 16 RF chains, the device maybe 4. So now the MIMO channel matrix is much smaller. So we could do this. We could do bit training plus a low dimensional channel estimation. But that's not ideal because we are not jointly defining the analog precoder and combiner, the analog and digital precoders and analog and digital combiners. We are first fixing the analog stage, and then we are deciding for that analog stage, which is the best digital one. And that's not the best way to maximize the data rate we can get. So channel estimation, and when I say that, I mean estimating the MIMO channel, the high dimension MIMO channel between the antennas at the transmitter and antennas at the receiver, is much more interesting because if you have all the information about the channel, you can jointly configure the digital and analog precoders and combiners. And there are optimal, suboptimal solutions to do that maximize the rate. So this challenge is about channel estimation, how to estimate the high dimensional MIMO channel with low overhead, very few training symbols, for example. In model-based approaches, people has been proposing different solutions to reduce the overhead. Some of these solutions just exploit the channel structure at millimeter wave. The channel is sparse, at millimeter wave. The scattering is not that rich as at low frequencies. There are few clusters, there are, let's say, a few sets of groups of directions of arrival and directions of departure. So there is like many holes in the angular domain, and we can exploit that to use compression sensing techniques to estimate the channel with lower overhead. Another thing that people has been doing is to look at the problem from a statistical point of view and use distributions for the different parameters, distributions for the angles, for the angle spread, for the gains, for the powers corresponding to the different clusters. And the 5G channel model provides information about all these. So it's not that the signal processing people working on these applications have come up with just models that work well with the mathematical approach they have. You can really use the statistical descriptions that are already in the channel, in the 5G channel model. And the description is very detailed there. I mean, it's not only that we know that it's a Laplacian distribution for the angle of arrival in azimuth, for example. I think it's elevation, sorry, for example. For azimuth is Gaussian wrap. We know the parameters, we know the deviations depending on the scenario, if it's macrocellular or if another type of scenario. So we really have a lot of statistical information about the channel. But obviously that information is not adapted to a specific site. It could be further refined if we have information about the site. We can have a better adjustment of the parameters of these distributions. And another thing that people have been doing to reduce overhead is exploiting out-of-band information. For example, using the position of the device to reduce overhead, or using the low frequency communication system, or using a radar at the base station to get information about the environment. So all these are possible approaches, and there is work, I think very, very interesting work on this area. We are able, I think, to estimate the channel with low overhead at this point. And we are also able to track the channel when there is high mobility with low overhead, as low as a very few symbols. So the question is, what can we do with machine learning? Is it possible to beat these other strategies? Maybe not in all environments, maybe not under all the circumstances, all possible scenarios, but the goal of the challenge is to understand this well. If we consider now a machine learning approach, which is site specific in this challenge, we are going to have a base station, and the machine learning approach is going to learn the structure of the propagation environment, basically, from the data. This can be a lot of received data through different propagation channels. So if we are able to generate this large amount of data, that large amount of possible channels corresponding to a given site, we can design machine learning strategies that use both offline training or online training, or just one of them. But we have to be aware that right now the machine learning approaches are site specific, and if you train the network to estimate the channel in a given location with some given data, probably most of the approaches we can see in the current literature are not going to work if I move the site, if I try to transfer this knowledge to another site, and we need to retrain. So it's not an obvious problem. It's not easy to solve. Here is the goal of the challenge. We are going to consider hybrid architecture at both the base station and in this case, vehicles, because we store a lot of channels, a huge number of channels using vehicles. But it doesn't really matter because it's initial channel estimation. So the mobility here is not going to play a role. We are not going to try to do channel tracking. We just have snapshots of the different possible channels, considering that the vehicles are located at different points in a given road, in a given site. These channels that we collect and they receive training pilots through that channel can be used to learn the environment for machine learning approaches and to train a given network, or can also be used by model-based approaches to refine these statistics I was talking about, or to learn, for example, some given sparsity patterns that can also be leveraged by model-based approaches. And then we will have to test the trained network using all these received symbols with different SNRs and low SNRs, because this is initial access. Again, the antennas are not aligned, so the SNR is going to be low. We cannot test the machine learning approach or the model-based approach with an SNR of 10 dBs. It's not realistic. And the idea is to test any possible approach that you can propose in a realistic scenario: low SNR, large number of antennas, few training symbols. How did we generate the data sets for training and testing? Well, here we have been working with Professor Aldevaro Glato at the University of Federal de Pará in Brazil. And we have been using the servers at UT Austin and also in Brazil to generate all these channels. And Aldevaro has been hosting all the data that, well, a lot of his students and a few of our students have been collecting, and they are hosted there in this web page that you can see there. There is also a paper that describes the methodology to generate all this data. And in this figure, I will try to summarize quickly what we did. Basically, Aldevaro was leading all this part and putting a lot of effort. So we use ray tracing to generate all these data sets. It's the most realistic thing we can do. We cannot generate 100K channels or 10K or 40K doing experimental measurements with a channel sounder. It's very, very time consuming. It's basically almost impossible for us from academia. We cannot put all those resources. So ray tracing right now is very well developed. There are very interesting tools, and we in particular chose Wireless Insight that has all the possible features that can be used for millimeter wave light diffuse scattering, for example. So it's a very interesting electromagnetic simulation tool that can reproduce very well the behavior of the electromagnetic waves at millimeter wave. And we have been using realistic scenarios from satellite data. We have been using Sumo to simulate the traffic patterns and the amount of cars, where they are placed, how they move. And we have all these packages interacting to be able to generate all these different channels. Once we collect these channels by ray tracing, then we can use MATLAB or Python or any other software you want to simulate the communication system. In fact, as I will describe later, for this challenge, we are going to use the channels obtained by ray tracing and also some MATLAB functions so you can generate the receipt pilots from the channels. And well, with that information, we are able to test and adjust model-based algorithms or machine learning algorithms. The data sets that we are providing for training consist of a collection of 10K channels in HDF5 format, and they are coming from this RayMobTime data set that I was describing before. In that web page, there are many data sets collected with different parameters. And in particular, we choose the one labeled as S004 because it's very interesting for this particular application of initial channel estimation to maximize the incoherence between the different channels that we have in the data set. And the idea is that you are going to get the channels and also the MATLAB code to generate the receipt pilots, 100 for every channel, when we use a MIMO FVM system and a hybrid architecture. So we are giving you the MATLAB code for this block diagram that you see here when we use a MIMO FVM system. You can play with the SNR, and you have to generate 100 receipt pilots using that MATLAB code. You just have to run it and choose one of the SNRs that we propose. And we were doing this because we didn't want to have to store 100 receipt pilots for all the 10K channels. It's much easier if you don't have to download those files because it would be really very, very huge. So for testing, we are not going to give you the channels. We are just going to give you a 9 collection of training pilots. So basically, we have generated 1,000 different channels, different from the one for the 10,000 that we had before from training. These 1,000 channels correspond to SNRs ranging from -20 to 0 dBs and correspond to the same site. That's going to be positive for the machine learning approaches. And we have these 9 different collections of training pilots because each collection corresponds to a range of SNR and a given number of training pilots. And we consider 3 possible values for the number of pilots and 3 possible ranges for the SNR. That's why in the combination we come up with 9 possible testing data sets. How are we going to do the evaluation? Well, when you submit your solution, you will have to send us the estimated channels for those testing pilots that we are providing. And the metric we are going to use for quality is the normalized mean square error. It's the usual metric in all the channel estimation papers. But when we compute the final score, we are gonna weight in a different way the results that you give us depending on the SNR and on the length of the training data. For example, we are given the highest weight to the data sets for testing that have very few training symbols, 20, and the lowest SNR. So when we have this SNR1 corresponds to the lowest possible SNRs, lower than minus 12 dBs, I think. So we are giving all the highest weights to that configuration. And then in this other test data set, 1 SNR3, for example, we have the highest SNR. So we still give a lot of weight because of the training, but less weight because of the SNR is high. These other training data sets in the middle, they have 40 symbols for training, and again, SNRs ranging for very low, so we give a weight of 0.5 to higher SNRs, always below 0, we give 0.2. And obviously, when we have many more trainings, online training symbols, this is what I mean by 80 training symbols is only for online training. Well, we give less weight, and this is the data set for testing that contributes the least to the final score is test data set 3 SNR3 because it's using the highest possible SNR and also the highest number of training symbol. So everything is ready now. Training and testing data sets are ready. The MATLAB functions that we provide are ready in our webpage. You have to register in the ITU webpage. You also have to send us an email to this address for enroll your team in our particular challenge. And you have to do both things. It's not just one. And then, well, the global run submission and award, that depends on ITU, and you will get more information later. And that's all from my side. I will take questions now and we'll try to clarify any possible information which is not clear in the webpage or that I did not explain well in my talk.
Thank you so much for this interesting talk. And now we have some questions. So we are going to go direct into the Q&A session. So I'd like to invite my colleague Vishnu to take over for the Q&A session. So it's up to you now, Vishnu.
Thank you, Thomas. Excellent talk by Nuria. Thank you so much. I have a bunch of questions here, which the first one being, are there 10K channels for each subcarrier?
Yes, we provide the channels, but we provide the channels in terms of the parameters of the different rays, the gain, the delay, the angles of arrival and departure for all the possible rays in our channel. And then in the MATLAB function, we apply the specific array geometry that we are using to that channel, and we have a frequency selective channel model. So yes, we have 10K channels for each subcarrier. The channels among subcarriers which are close are quite similar, obviously, but yeah, the answer is yes.
Thank you. And the second question is, how many antennas at the TXRX are considered for training and test data set?
Okay, let me check. Let me check the MATLAB code. We were testing on 128 and 64, and let me check now which one I left at the end. I just need to check quickly the
While Nuria is checking, please use the Q&A button for the questions.
You mean you want me to write the questions? The answer?
No. I was telling the participants to use the Q&A. Please
Okay.
go ahead. Go ahead and please.
So yeah, we are using 64 antennas at one side and 16 at the other side. So that, but that's specified in the MATLAB function that we are providing, 64 and 16.
Thank you. And the next question is, solutions do not necessarily have to be based on machine learning technique. Conventional signal processing techniques are allowed or not?
Yes, correct. It is correct. What we want to do is, you know, is not using machine learning for everything. I had a cartoon in the Signal Processing magazine about this hype with machine learning 4x in that cartoon. It's just, you know, let's use machine learning when it's outperforming other approaches, and there has been a lot of work on more conventional signal processing approaches. And the idea of the challenge is to say, okay, what can be gained with machine learning? Because signal processing approaches have a clear advantage, which is they are not site specific. That's very clear. If we made them site specific, they are gonna perform much better than we have seen in the results in the papers. Because in these results, we usually evaluate the algorithms with a lot of channels coming from a statistical channel simulator that doesn't correspond at all to the same site. So we are establishing here the same conditions to evaluate machine learning or signal processing approaches. And we are also giving the signal processing techniques the ability to exploit data, because exploit data, if the data is going to be available, we don't have to solve the problem only exploiting those data with a deep neural network, for example. We can use a statistical signal processing approach that can also learn distributions from that data. It wouldn't be fair just to say, okay, well, I can only use machine learning here. No, you can also use other tools. And the idea is to understand how far we can go with both types of approaches. The training symbol is a matrix or a vector. So we are having two streams in the MATLAB script that that is available in the web page. So we are training for every time that we send something, it's two strings. So we have to send all this information. The size of the channel matrix is 64 by 16 because that's the number of antennas that we are choosing. But all that is clearly specified in the MATLAB file.
Okay, seems like Vishnu dropped off a little bit, so I can take over. And so we have another question here. It says, if I understand correctly, solutions do not, okay, we have taken this one. Let me go to the next one. Is the training symbol a matrix or a vector? And what is the size of the channel matrix?
I already replied to that one.
Ah, okay. And if signal processing techniques are allowed, they can't get lower of Cramer bound. So they can't be better than machine learning.
Well, I don't agree with that statement at all. So yes, we have a Cramer lower bound, but what's the bound for machine learning? I mean, I have not seen so far machine learning outperforming signal processing. They can perform more or less well, and then there is not only the fact of which is the minimum mean square error that you can get, it's also how much training do you need, because if you need an infinite amount of training, this is not practical. So we are comparing both types of techniques exactly with the same in the same setup with the same performance score. So I think it's a fair environment.
Okay.
Thanks.
In
Thanks
fact,
so much.
it's more, let's say, it's unfair for signal processing, because all the signal processing techniques, unless you really adapt a lot, the parameters, the patterns, the sparsity patterns or anything can be used in any site. While machine learning so far cannot be used in any site. Needs the data collected in a specific base station or access point.
Thanks. Thank you so much. Sorry, I am back just in time, maybe to ask the next one. Is there any, is it allowed to generate additional data set in cases where algorithms
No,
require sampling?
no. The answer is no.
Okay. And the next one, is there any weightage for complexity or size for the neural networks?
I lost the sound for a while. What's the question again, please?
The question is there any weightage for complexity or size of neural networks?
No, we are not, let's say, considering that. We are just considering performance. We are not considering complexity.
Mm-hmm. And if I can ask, maybe you answered this in the presentation. What let us say I'm a participant trying to submit my solution. What kind of, how can I win? I mean, what is the differentiating factor? So when you see a submission, right? So you go like, wow, okay, this is the top entry for me. As a judge, when you look at it, this is a top entry for me. Or when you say, okay, this is good, but you know, maybe comes next. What makes the difference? What are you looking for?
Well, my main goal, I've been publishing solutions on both approaches. I have more work on signal processing approaches. And my main goal is to ask the machine learning people to compare to the right approaches, because we are seeing some machine learning papers on channel estimation that they do not compare at all with the state-of-the-art solutions. They compare with very basic signal processing techniques like least squares, which obviously do not perform well at millimeter wave frequencies with these large matrices. So my goal, I'm interested in both approaches. I'm working on both sides, and I want to be fair. I have a scientific perspective, and I want to say, okay, you know, I'm trying to make a fair comparison. I know there is some unfairness due to the site-specific feature of the challenge, but because it's true, one of the questions I see there, it's true that a machine learning approach can perform very well in a site, and then you just translate that architecture to another one and it doesn't perform well. That happens all the time. But let's give a little bit more of time to machine learning to propose more solutions. Conventional signal processing techniques have had a lot of time in the last years to propose solutions. Machine learning is starting, so let's define an environment, a setup, which is not unfair for machine learning because it doesn't have the maturity for this problem. And signal processing can also benefit from the training data. The data is there, and you can learn things from there, from sparsity patterns to statistical distributions or parameters of those distributions. So I know it's not exactly completely fair. It helps machine learning, this environment, but we also have to be aware that probably all these data are going to be available in the base stations. So why not machine learning?
That's a really good answer. And thank you for taking that. Next one, there are other challenges, for example, based on beam tracking. There are some challenges. It appears that based on beam tracking, how is this challenge different from that?
Okay, beam tracking, as I said, is usually applied to analog architectures, analog MIMO architectures, not hybrid. If you want to configure a hybrid architecture, you could use beam training, it's not optimal, you could use beam training to configure the analog, and then you could estimate the low dimensional MIMO, equivalent MIMO channel to configure the digital precoder and combiners, but if the challenge is only on beam tracking, then it's only on configuring the analog precoder and combiner. It's just one string, it's just one RF change. It's a bit, the problem is a bit simpler. Well, this is being promoted by Ahmed Al-Khatib. I think he was a student of Robert Heath. That I also have some papers with him. He started to work on ray tracing and all this with us before at UT Austin. Now he's in Arizona State, and he's trying to also lead this topic there. But the challenge is different. The problem of beam training is choosing a beam pattern from a possible set of beams available in a codebook. In channel estimation, you have to estimate the gain, the delay, the angles for every path in the channel. And then with that information, you configure the digital and analog precoders. With beam training, you select a beam for the analog and for the analog precoder and the analog combiner. So it's very different.
Thank you. If there are two submissions, one conventional signal processing based and another ML based, which achieves the same performance, which one wins?
Okay, I think in that case, I've already, I cannot change. I didn't consider that solution because it's really, that possibility, so because it's really very difficult that perform exactly the same way. But if they perform very similar, what I would do is to test the machine learning solution in a different site and test the signal processing solution in a different site, and probably conclude that the signal processing solution wins at this point. I don't know what the participants have in mind. Maybe they have a solution that can be translated to different sites. I don't know. But obviously that's the way to differentiate between two solutions that perform very well in the same site. Well, for this challenge, I would say both of them win. We can give like a bonus to the one that performs better in a different site. I could do that, and I could add that to the website if that's of interest. I mean,
sure, yeah, sure. I think that you know, the reason for ITU to do this kind of challenge is to do this kind of comparison, but at the same time we are interested in pushing the envelope as far as machine learning is concerned.
exactly.
So yes, exactly. I agree with you.
I know how to
Generalization.
do. I know how to do further.
Exactly.
So I could change the page. We can discuss it, and I could change a bit that, just in case there is a similar performance to have a different.
Sure. Yes. I think this is interesting question. Yes. Next question is, are the phase antenna vectors, there's weights for the antenna analog beamforming, generated randomly for the training data or based on a specific code book?
They are generated randomly. So they are also available in the MATLAB code that is provided. It's available how they are generated.
Very good. Yes. You mentioned MATLAB codes for the system model, etc. Could you provide details on how to access the codes? I think this I have seen you have it already in the website.
Yeah.
Yes, yes. Okay,
You just
I
have
will.
to download from the website.
So
There.
I think you should go to the website and you can access the MATLAB code directly from there. Next question is SNR levels proposed. There is -20, -15 seems very low. Do you provide code to compute such SNR levels in MATLAB code to validate such levels from preamble signals?
Yes, that's included in the MATLAB code. And yeah, I know it looks slow, but it's reality. That may appear in a realistic millimeter wave scenario.
Sure. Yeah, I also want to at this point refer to Professor Aldebaro's presentation last week.
Yeah.
He gave an excellent presentation about the data set, which is actually reused. The RAMOP time is reused between the two problem statements. So if you have not if the participants have not looked at that one, we have a recording of this excellent talk which Aldabaro gave us last week. It is in our website. In fact, he gave some more details about the RAMOP time and how we also discussed during the question session with Aldabaro how the surfaces are modeled in the simulation. I just want to ask you, how much time did it take for you to generate the data set? I mean, it looks it looks quite complicated. So to use this setup, I know, I think Aldabaro may have covered it, but what do you think, what was the complexity? Could you give us a little bit insight on for your problem statement, how much time and how much effort did it take?
You mean generating the data sets for the channels?
Yeah.
Well, generating the data sets for the channels, once you have the setup created, can take weeks because it takes a lot of time to run the ray tracing for so many channels, so many possible locations of the receivers, and then once you have that, you have to create the real data that you use for training is the receive signal. So you need to create a MATLAB code to simulate the system, and then you need to read the channels that you store in MATLAB and run the MIMO FDN system and generate these receive pilots. You need to generate the code, and well, you have a good knowledge of what you're doing. It can take just a few days. That's what it took me, like a few days. It always takes more than you expect because there is always the format file problems or these versions of MATLAB or this version of the data, I don't know. And at the end, yeah, it always takes much more than you expect, but it's fine. It's funny.
Yeah, thank you for all the work which you have done for us. So yeah, I'm sure the participants would really appreciate the effort which you have put. Where do we go from here? I mean, so could you also tell us? We have few more minutes. Could you explain where do you take this research from here? Yes, we are having this challenge. What are your thoughts on the future? What do we do next from this challenge? Do you think of future things, future challenges? Where do we take this? Where do you see this research going from machine learning in this area?
Yeah, well, it's very clear that research has to go in the direction of developing machine learning solutions that can be reduced with very few additional training at different sites. That's the main challenge to me. And also Another problem with machine learning is that depends a lot on the system parameters. So if I fix the number of antennas at the transmitter and at the receiver, I'm fixing everything. I'm only allowing devices that fit those specific parameters. If I have a new device with a different number of antennas, I need to generate a different training data set. So to me, the path to move forward is to make machine learning solution less dependent on specific parameters of the system. That means the communication system itself, like number of antennas, number of RF chains, and also the specific location. That's the way to go.